All right, so let's pick up, moving from lecture one, which was just sort of like an overall framing. Now we're going to be taking these same ideas, but using more precise statistical language. Um, the vocabulary that we talk about here is going to show up throughout the rest of the semester. So the field of statistics is how to best collect, analyze, and draw conclusions from data. We can use it to compare things or to make predictions about the world. So the data comes from a range of sources, so things like field notes, surveys, and experiments. Each of the sources will require us to use different tools and worry about different shortcomings. So for field notes, think about fields like psychology or anthropology, where you want to dig in really deep, get a lot of information, a lot of it not numbers, but qualitative data about very specific things. Moving on to surveys, this is something that, as an economist, I use all the time. So there are a lot of government surveys that are run on, say, 1% or 5% of the population, asking them a series of questions about themselves and the people in their households. That's something that I use all the time. It can be really difficult, time-consuming, and expensive to run your own surveys. So oftentimes we rely on surveys that have been done by others, like the government or Gallup. Tons of different organizations that are large have the ability to run those. And finally, we have experiments. And this is what we think about for hard science. So maybe vaccine clinical trials. This is the gold standard of what we want to see with statistics. Field notes are great, surveys are great, they have their uses, but experiments really help us identify the cause and effect that's going on. They're much harder to run, they're very expensive, but they yield better, more trustworthy results. So let's look at an experiment from the chapter. Does a stent reduce stroke risk? Now, in this study, we have 451 at-risk patients, and they're randomly assigned between the treatment group and the control group. This is very good. That's about the equal number of people. Random assignment, great. The only planned difference between the groups is the stent itself. So everything else, the medication they take, the risk factor management, this is all held the same, or they try to hold it the same. And this is why experiments are so powerful. The goal is to remove all the difference so that the only change that you see is a change that you're studying. So in this case, the only difference is putting in that stent. This way, you can be sure that the effect that you see is a result of that intervention and that intervention alone. So the experimenters set this up with a group that receives the treatment and one that does not. The one that receives the treatment we call the treatment group, and the one that does not receive the treatment we call the control group. In the best trial, the participants don't know whether they're the treatment group or the control group. And neither do the experimenters who are dealing with them, who are talking to them. So they don't, accidentally kind of tip to them or show to them um, whether they're the treatment group or the control group. So what do we see? Here are the results. We see that the treated group who received what should have helped them ended up with more strokes. So they had 20% of them having a stroke within a year, whereas there were only 12% that had a stroke in the control group. So we just set up the stent study. 224 patients getting a stent, 227 getting the medication alone. Um, so our prediction, if we thought about this ahead of time, if I didn't show you the results yet, would be that stents would help. That's the whole premise of Ezone. That's why we would use it, is so you would expect a lower stroke rate in the treatment group relative to the control group. So researchers found the opposite. The group that got the stent had 20% of the patients that had a stroke within a year. The control group only had 12. 20% versus 12%. That's the opposite of what everyone expected. The group that got the intervention that was supposed to help them did worse. So here's the question that separates a statistics class from a quick gut reaction. Is that 8-point gap a real effect of the stent, or could it just be random noise, or could there be something wrong with the experiment? Think about flipping a coin 100 times. You would expect 50 heads, but you might get 54. No one would really call that suspicious, a slight difference around what the expected outcome would be. But this is an 8-point difference in the opposite direction. Is it the medical equivalent of getting 54 heads instead of 50? Right now in week one, we don't have the tools to formally answer that. That's going to take us into the inference chapter, and that's going to be later in the course. But the published analysis on this actual study concluded that there was compelling evidence of harm. The difference here was just too largely explained away as chance. So let's sit with the question there ourselves for a second and think, does seeing a gap in the data is seeing a gap in the data the same as proving the gap is meaningful? So is this effect real or is this just noise? This is the type of question that's going to come up constantly over the semester as we're walking through these examples. Now, before we move on, I just want to touch on one more thing. This study looked at a specific group of at-risk patients and one specific brand of stent. So it would be a mistake to apply this outside of the very narrow focus, and thinking stents are dangerous for everyone, always. So good statistical thinking means being precise about who a result actually applies to, not just saying what the result says, just spitting that out. So it could be that that particular brand of stent is lower quality and dangerous. Maybe it's the procedure they're using to put it in. Maybe there really was some difference in the group that they didn't notice ahead of time. We'll have to think about that, and we'll explore these sorts of things more throughout this semester. Now, before we move on, I want to slow down and get more precise about the vocabulary that we're working with. So I'm going to use these words constantly, and you'll be using them in your writing and some of your assignments. So I want to make sure that we know all these words. So I want you to look at this table here on the slide. It's a small piece of a real data set that Open Intro uses. They call it Loan 50. So 50 loans from a peer-to-peer lending company. Each row here represents one loan. So in statistics, we call a row like this a case or an observational unit. It's the thing that we're studying. Here, a loan. In the stent study, it would be a patient. In your problem set this week, it might be a sales rep, one of those questions. Now, look across the row instead of down a column. So across the row, we have the loan amount, the interest rate, the grade, different characteristics for that. Each of these columns, each of these characteristics is a variable. So a characteristic that gets recorded for every single case. So each loan has an amount, every loan has an interest rate. That's what makes it a variable, not just a random fact about a loan. And when we take this whole column and we boil it down to a number, say the average interest rate across all 50 loans, we call that a summary statistic. We've actually met summary statistics in the last lecture. The passer rating, the Gini index, those are summary statistics too. They're just a little bit different. If you remember nothing else from the slide, remember that rows equal cases and the columns themselves equals variables. Every variable you will ever encounter in this course splits into one of two families. They'll either be numerical or categorical. So let's go down each branch. Numerical means the values are numbers. And this is the important test, not just that they are numbers, but that it makes sense to do math with them. If I can compute an average, a numerical variable is probably the right call for a variable. But now you can split numerical again into continuous and discrete variables. Continuous means a variable can take any value in a range. So things like height, temperature, the unemployment rate. There's no smallest gap possible between two values. You could always measure more precisely. Discrete means that the values jump. So you may count in whole numbers. So say number of siblings. You have either one sibling, two siblings, three siblings. You don't have 2.5 siblings. Now the other family is categorical. These are variables where the values are labels or categories, not numbers that you would work with. So the state, that's a categorical variable. Homeowner status, rent, own with mortgage. These are categorical variables. Even if a categorical variable is coded using numbers, so like a zip code or a state FIPS code, averaging those numbers would be meaningless. That's how you know it's a categorical variable. And again, we could split categorical variables into two variables. Nominal, where the categories have no natural order. So a state is a good example. Ohio is in more or less than Maryland. They're just two different states. And then there's ordinal, where there is a natural order to the numbers, even though they can't be added together. So education level is a textbook example. So you have below high school diploma, some college, bachelor's. You can rank those in order, and that ranking actually means something. Here's the mistake I see most often. Students see a number and they assume numerical. That's the easiest one to make. A zip code is a number, a state's zip code is a number, but it's categorical because you wouldn't average the two of them together and expect that to mean anything. So a good reality check when you're trying to determine what sort of variable, how to classify a variable, what sort of variable it is to think, does averaging this variable produce something meaningful? If the answer is yes, it does produce something meaningful, then that's a numerical variable. If the average would be nonsense, then it's a categorical variable, no matter whether it's written in words or numbers. So let's talk about the distinction that sounds small but causes a lot of confusion later on if we don't internalize it. Explanatory versus response variables. When we suspect that one variable might affect another, we give them names. So the variable we think is doing the affecting is the explanatory variable. The variable we think is being affected is the response variable. In our county example, the median household income is explanatory. The population change is the response. Because our working theory in this example is that richer counties might attract more people. More people want to move there, not the other way around, people not wanting to move to a depressed area. Now, here's the part I really want you to hear carefully. Labeling a variable explanatory does nothing to actually prove that it explains anything. It's a hypothesis at this point. It's not a finding yet. We haven't proven anything, but we think that's the relationship. So you could be wrong about the direction. You could be missing some third variable that's impacting both of them. We're going to see exactly this problem later. But notice something else. For a lot of variable pairs, there's no hypothesized direction at all. Maybe there's no relationship at all. If I give you two variables, say sales reps favor color and their shoe size, you wouldn't try to label one an explanatory variable and one a response because there's no plausible story connecting them. Same thing if you look at data plotting the number of shark attacks in the US and Nicolas Cage movies. There's actually a really strong relationship between the two of them. The numbers seem to move together, but there's no story connecting them. So the labeling explanatory and response variable only applies when there's a real hypothesis on the table, something that seems reasonable. Later on, when we get to regression analysis, you're going to be building models with explanatory variables that predict a response variable. If you walk into that module thinking explanatory variable means it's proven already, you're going to misread your own results. Now, I mentioned a little bit earlier about observational studies versus experiments. So observational studies, researchers collect data without interfering, without doing anything to how the data arises. So these are like surveys, medical records, things that are being done after the fact. Nothing here is being designed by the researchers. Using observational data, we can show associations. We can provide some evidence of a relationship, but we cannot, using observational data, prove causation, prove that one variable impacts another. On the other hand, we have experiments. And in this case, researchers design what's going on with the data. They assign a treatment to one subset of people and set the other subset as a control group. So we want to see if that treatment affects the response. So think of the example for the patients with the stent versus no stent. In this case, when individuals are randomly assigned to the treatment group or to the control group, we call it a randomized experiment. Again, this is the gold standard. This can show causation. It's not just providing evidence. You can, if it's well designed, you can prove causation. Now, people like to say correlation does not equal causation and kind of shut down a debate. And we're going to talk about this a little bit more later in the course. Right now, I'm going to agree with that and say association or correlation does not equal causation. So let's say researchers look at a large group of people and found that the more sunscreen someone used, the more likely they were to have skin cancer. More sunscreen, more skin cancer. Think about that for a second. That's the opposite of what you'd expect. If you didn't know anything else, what would you conclude? It'd be tempting to say that sunscreen causes skin cancer. Maybe there's a chemical in it. Maybe it's not blocking the thing that causes skin cancer. Maybe we've been doing things wrong the entire time. But we've seen a lot of other research that does show that sunscreen reduces skin cancer. So maybe in this simple experiment or the simple description of an experiment, something's broken. So the question is, what are we missing in this picture? So the answer could be sun exposure. Think about someone who uses a lot of sunscreen. If you use a lot of sunscreen, odds are you spend a lot of time in the sun. If you're not using any sunscreen, maybe you're going out in the sun, maybe you're burning all the time. Maybe you're going out in the sun, but you don't need sunscreen, so you're not burning. Or something's very likely is you're not going out in the sun at all, or you're going out very randomly. So you're not putting yourself at risk. So the group that's using sunscreen, they're getting more skin cancer because they're spending much more time in the sun anyway. So you have sun exposure driving both variables. Sun exposure is increasing sunscreen usage amongst the one group and is pushing skin cancer up, completely independently of whether the sunscreen itself does anything. So here we have the diagram here, kind of showing this visually. So the sun exposure is sitting at the top with the arrows pointing down to both sunscreen use and skin cancer because it's impacting both sunscreen use and skin cancer. So the direct arrow we'd love to draw over here that the use of sunscreen causes skin cancer is the dashed line with the question mark because it really doesn't actually exist in this example. We call the sun exposure a confounding variable. Sometimes we call it a lurking variable to express the sort of danger. We don't see it, but it's there. So it's a variable that's connected to both the explanatory and the response variable. It's driving both of them. It's creating an association that looks causal, but it really isn't. So it's the same thing we talked about with the example of the short breaks causing cancer story in the last lecture. Remember, 10-minute breaks looked like they caused cancer until you realize that those breaks were people smoking. So it was the smoking that caused the breaks and the smoking that caused the cancer. So it's the same pattern with a different variable doing the confounder. So going forward, anytime someone hands you an association, X is linked to Y, your next question should be, what's the sun exposure in this example? What third variable that they're not mentioning could be driving both of these at once? So let's cover the 4 ways we can actually go get a random sample. I'll give you the plain language handle for each one plus a quick example, because these are 4 terms that tend to blur together, can be difficult to pull them apart and distinguish them when you first see them. So first is simple random sampling. So think of a raffle. Every case in the population has an equal chance of being picked. If I wanted to survey 100 employees out of 3,000, I would literally put all 3,000 names in a hat and draw 100. That's simple random sampling. It's considered the gold standard for samples, but it's not always practical. So sometimes you have to use other methods. The next is stratified sampling. So first we divide the population into similar groups. We call them strata. And then we randomly sample within each group. So imagine if you're sampling baseball players' salaries. You split them up by team or you stratify them by team, since some teams have bigger payrolls than others. Then you randomly sample a few players from each team. And the keyword here is every. Stratified sampling touches every single group. You could also try cluster sampling. This one is the opposite of instant. So instead of touching each group a little, you divide the population into clusters and randomly pick a few whole clusters and measure everyone inside those clusters. And you skip everyone in the clusters you didn't pick. So imagine going overseas and you're surveying malaria rates across 30 villages. So instead of visiting all 30, which might be impractical, maybe they're spread out really far, maybe there's no like real roads in between them, you select 10 villages randomly, and then you test every person in those 10. And finally, there's multi-stage sampling. This is very similar to cluster sampling with a twist. So instead of measuring everyone within each chosen cluster, maybe those clusters are large, you then randomly sample within those clusters too. So say you're looking at those same 30 villages again, but the villages are fairly large. So you pick 10 villages randomly, and then within those 10 villages, you randomly sample some of those people instead of all of them. So the distinction that students often mix up is the stratified versus the cluster. So here's a clean way to think about it to keep them apart. Stratified sampling reaches into every group. Cluster sampling reaches into only some groups, but it goes all in on the ones it does pick. So it's the same underlying idea that you're first dividing into groups, but it's opposite in the way that they go within those groups and select from within those groups. So let's take stock of this lecture. So we've talked about a bunch of terms, 9 terms that I want to focus on here that are going to reappear throughout the rest of the semester. Run through them very quickly, just to kind of summarize what we've learned. So the case or observational unit. This is one row in your data. A variable. This can be numerical or categorical, but it's one column in that data matrix. The data matrix is the entire table, the rows as cases and the columns as variables. Next, the population versus sample. The population is the whole group that you care about. The sample is the smaller group that you actually collect data on. Next, association and independence. Do two variables move together or not? Are they related or are they not related? It's the same kind of idea here for explanatory versus response variables. If they are related, which variable do we think is doing the affecting? And which one is being affected by a change in the other variable? Now, observational studies versus experiment. Did the researchers just sit back and watch, look what happened afterwards, and collect data on that? Or did they design it and really assign who is going to get treated and who is not going to get treated? Confounding variables. Remember, these are the hidden third factors, the lurking variables like sun exposure that can make an association look causal when it really isn't. And finally, randomization, binding, and placebo. These are the tools that researchers use to make sure an experiment's results are trustworthy.